Assalamualaikum and a very good day. My name is Nurul Iman binti Muhammad Sofi. In this video, I would like to make a short demonstration regarding my final year project about cross-connected source multi-level inverter. This project is supervised under Prof. Madya Dr. Syahrin bin Mak Ayub. First of all, cross-connected source multi-level inverter is an alternative for multi-level inverter circuit. Before, there are a few conventional topologies and the most common are diode lamp, sine capacitor and cascaded bridge. The multi-level inverter has been very popular for high power and medium voltage applications because of the ability to create a high output voltage with high efficiency and low harmonic distortion at the same time. However, to achieve this, lot of switching devices are required, so it will lead to a higher cost, size and complexity of the design. Hence, a new topology is proposed, which is called as cross-connected source multi-level inverter. The proposed inverter can also create a high output voltage but with less number of switches. In this video, we will see how both of the conventional topology, specifically the cascaded bridge and the new topology cross-connected source, actually works. We will also analyze all the performance, including with various modulation index. All the analysis are focusing through simulation only by using Simuli MATLAB. The simulation is started by creating a signal pulse for the switches. The circuit shown here is a multi-carrier pulse width modulation (PWM) circuit. The essential thing for PWM circuit is the modulating signal and carrier signal. In order to create 5 level output voltage, 1 modulating signal and 4 carrier signal are required. Each 4 carrier signal will have the same value of amplitude and frequency. Here is the parameters that been used for PWM technique. Later on, the same circuit will be used for both cascaded bridge and cross-connected source multi-level inverter as their switching pulse. After running the program, we can obtain the switching pulse for each switches. The next one is cascaded bridge. Here we can see we are using the same PWM circuit for switching purpose. We also included the same value of modulation index as we have seen before. Each pulse created are connected with the respective switch. For 5 level output voltage, cascaded bridge needs total of 8 switches and 2 DC source. The parameters that have been used are as follows. We are using resistor and inductor as the load and IGBT diode block as the switch. To get the voltage measurement, we need to run the simulation, and here shows the output voltage and output current waveform. For the output voltage, here we can clearly see the 5 level of voltage started with 200 volt, 100 volt, 0 volt, negative 100 volt and negative 200 volt. As shown, the THD value obtained for cascaded bridge is 26.7% with fundamental voltage equal to 200 volt. Now, we move on to cross-connected source multi-level inverter. Similar as previous bridge inverter, the same PWM circuit are being used. The only difference here is the additional logical component to ensure that each switch will have the desired switching pulse. Since the requirement number of switch is 6, the original PWM pulse have been derived to create from 8 to 6 pulse by using K-mat method. This is to ensure that the process of close and open switch will be accurate and follow the switching state. For 5 level output voltage, cross-connected source will be need the total of 2 DC source and 6 switches only. All the parameters are using the same value as bridge since we want to compare both of the output result later. After running the simulation, we obtain the output voltage and output current waveform. Based on the result, there is the 5 level voltage which is 200 volt, 100 volt, 0 volt, negative 400 volt and negative 200 volt. And the measurement of the THD value is 26.67% with fundamental frequency equal to 200.3 volt. If you compare, both of the multi-level inverter has successfully created a 5 level output voltage waveform. Also, the THD value of cross-connected source is slightly smaller than bridge, but we can assume that the value is almost the same. This is because both of the multi-level inverter are using the same value of modulation index. Then how about in terms of voltage trace? To measure the voltage trace, simply use the voltage measurement block to each switch and connected them all in the scope to observe the waveform. After running the simulation, here we can see the value of voltage flow across them. The same procedure are applied into cross-connected source circuit, where each IGBT diode block are connected parallel with voltage measurement. From the result, we can observe that all the voltage stress in hash bridge inverters is equal to 100 volt, while for cross-connected source, the highest value of voltage stress is 200 volt. This is because when less switch components are used, the voltage across the switch will be much higher and also increasing the voltage stress, which is one of the disadvantages of this topology. Total harmonic distortion voltage can be varied with various amplitude modulation and frequency modulation. In this simulation, for amplitude modulation analysis, different values of modulating amplitude are used by keeping the amplitude of carrier signal fixed. For example, with cross-connected source circuit, the amplitude are being changed here. After running the simulation, here we can see the new pattern for modulating waveform. The output waveform and THD signal also changed. The same procedure are being used with different number of amplitude as in the table. We are not using MA larger than 1 because overmodulation will happen. Based on the result, we can observe that all of the output waveform have 5 level voltage except for the one with MA equal to 0.4. Next one is frequency modulation in analysis. Same procedure are being used, but here we are changing the value of carrier signal frequency from 500 Hz to 5000 Hz. At the same time, keeping the modulating frequency fixed at 50 Hz. As a result, the triangular waveform are changing, which also changing the output voltage waveform and THD spectrum too. Here we can observe when the MF is increased, the first harmonic frequency is also moving far from the fundamental frequency. Hence, the larger the distance, the easier for the harmonic filtration process later. Lastly, to produce smaller total harmonic distortion, the MA must be large or equal to 1 and the MF must be smaller. That's all from my demonstration with MATLAB. Thank you for your time.